Hello, my name is Keith Litch. I'm a customer support engineer here at Keysight Technologies. I received a question from a solution engineer asking me how I would make an occupied bandwidth measurement at 84 gigahertz for an FMCW signal. And so here to show you what my recommendations are. I have a N9042B UXA along with its frequency range extender that extends the frequency up to 110 gigahertz. To generate my FMCW signal, I have a M8195A arbitrary waveform generator. I'm using IQ tools. I'm generating 300 550 microsecond pulses. We're doing that for 15 milliseconds and then an off time of 35 milliseconds for a total duty cycle of 50 milliseconds. I'm using a PSG to generate my 40 gigahertz LO for my up converter. The LO is doubled, so that's 80 gigahertz plus a 4 gigahertz IF yields a 84 gigahertz signal. That's also 4 gigahertz wide, connected to my V3050A. And so I've preset my UXA signal analyzer. You can see the FMCW signal there. One question I get a lot is why the discrepancy or discontinuity in the noise floor between 50 gigahertz and below. Well, there is a first stage amplifier in the V3050 that lowers the noise floor. I can also lower the noise floor below 50 gigahertz by simply turning on the full range amplifier. The attenuation auto couples to a higher attenuation. I can set that down to 0 dB. And then now I get a pretty flat response. Let's go ahead and preset. So let's go to a frequency of 84 gigahertz. Let's go to a span of 4 gigahertz. And I'm going to turn off software preselection. Signal path, software preselection. So there's my signal. The V3050A has a bank of filters, which are pretty good as our preselector. It also has software preselection above 90 gigahertz. Software preselection is turned on by default. For this case, I don't need software preselection. So you can see my signal is pulsing. So how am I going to measure the response? Well, I have a duty cycle of 50 milliseconds. One way to make this measurement would be to simply slow down the sweep time so that each trace point bucket is measuring over the entire duty cycle. So I can do that. I can set my sweep time to 50 seconds. So 50 milliseconds times 1,000 ends up to be 50 seconds. I want to use peak detector. And so it takes a little while for the measurement to start. Oh, and I meant to set my span to 5 gigahertz. Span 5 gigahertz. So we're tracing out our signal. You can see this takes a while to make the measurement. Although the sweep time is 50 seconds, there is additional overhead for the sweep. So how can I do this measurement faster? Well, one way to make this measurement faster is to use LO gating. So for LO gating, I can use my RF burst trigger to train my periodic trigger. When I'm making really wide span measurements, my RF burst trigger doesn't have the bandwidth to see the signal over greater than 100 megahertz bandwidth. So if I use my periodic trigger, I can train it with the RF burst trigger and set my periodic trigger to trigger reliably every 50 milliseconds, and I could span out. So let's go to time gating. So let's first, let's set our sweep time back to auto. Let's go to 0 span. And then, so I could train my RF burst trigger 100 megahertz span or less. I could do it in 0 span. So I'm going to go to trigger, gate source. Let's use our periodic trigger as our gate source. Let's set the period that we want for it, which is 50 milliseconds. And then let's go to our periodic trigger. Let's use the RF burst trigger to to train the trigger. Let's choose a trigger level for our RF burst trigger of minus 40 dBm. So our pulse, we're FMCW chirping for over 15 milliseconds, and then we're off for 35 milliseconds. During that 15 milliseconds, my RF burst trigger will trigger multiple times. I don't want it to do that. I want it to trigger, and then I want it to not trigger until the next pulse happens. So I need to set a hold off of at least 15 milliseconds. Let's set a hold off of 20 milliseconds. And then let's go back to our gate settings. Let's turn our gate view on. And then for our gate view setting, let's look at two pulses. Let's look at double of 50 milliseconds is 100 milliseconds. So you can see this is our first set of 300 FMCW chirps, our second set. Then I can set up my gate. So I can choose my gate delay and my gate length. As a good rule of thumb, you usually want to gate over about 80% of the burst. And then I can actually turn on gating, turn off gate, turn on gating. It's gating using the RF burst trigger. So I want to, for my gate, I want to transfer the time for the RF burst trigger that happens in this narrow span. I want to use that as my time so that I can make use that as my trigger source for LO gating over the entire 5 gigahertz span. So I go back to my periodic sync source, and so I change from RF burst to off. And unfortunately, there's a defect right now where it didn't remember the time, so I can go ahead and I can adjust my periodic timer to move my burst back here. Okay, so now I'm using my periodic trigger, and then I can go back to gate settings, turn off my gate view, turn on gating. It's nicely gating, the signal's staying constant. Now let's go ahead and increase the span to 5 gigahertz. And here's my signal. Unfortunately, it's sweeping too fast. So that's another defect that's going to be fixed. So let's set our sweep time to 50 milliseconds. And now I'm gating, and my measurement is much faster than it was when I used a long sweep time of 50 seconds. I can go back to gating, trigger, gating. I can turn gating off. My signal is intermittently being captured. I can, instead of gating, I'm also able to, I could use max hold. Is another way to make this measurement, but then I won't see differences if the signal's changing. If I'm using max hold, I won't see differences from sweep to sweep. So instead of using max hold, I recommend using gating. Trigger, gate settings. We'll turn our gate back on. Okay, so here's our nice 4 gigahertz wide signal. So the question that I was posed with was how to make an occupied bandwidth. So we're almost there. For occupied bandwidth measurement, I will go to the occupied bandwidth measurement. I need to set my span back to 5 gigahertz. I need to go back to my detector. Oh, sorry. Go back to my trace detector, go back to peak detector. And unfortunately, we're sweeping too fast again. So let's set our sweep time to 50 milliseconds. And so voila, here's my occupied bandwidth measurement. My result is right around 4 gigahertz. And I was successful in making this measurement for this solutions engineer. The question was, are there other ways to make this measurement? And yes, we could use a down converter, a CCD down converter instead of the V3050A. And then the question was, can you use an external mixer? Can we use our smart mixer? Our smart mixer has an IF of 1.5 gigahertz. So it's image protected to twice that, about 3 gigahertz. So for this 4 gigahertz wide signal, it doesn't quite have a high enough IF to make the measurement. But for this particular solutions engineer, it actually worked okay, because the fold over region for the signal ended up being in the middle of the trace. And so the occupied bandwidth measurement was still pretty accurate on telling what the full, the 4 gigahertz occupied bandwidth for the customer. So that wasn't a complete solution, but it worked in that situation. Thank you for watching, and I encourage you to look at some of our application notes. We have an application note on time gating that is very useful to go through to understand time-gated measurements. Otherwise, thank you very much for watching this video.